This is the video for Unit 4, Episode 503, and this is the one on molecular geometry. So first of all, when we're talking about the shapes of atoms and molecules, if you have two atoms bonded together, then no matter what, they're going to make a straight line, and we call that a linear shape. So anytime we have a molecule with two atoms, we get a linear shape. And so that's the simplest one. This would be a 180-degree angle for the bond. So if you look at it like hydrogen and chlorine, no matter how we bond those, to get the electrons as far apart as possible, they're going to be a straight line. So that's what a linear shape is. When we have two or more atoms, when we have more than two atoms, we use the VSEPR theory, and it's right over here. So that is valence, shell, electron, pair, repulsion theory. And what that means is the electrons that are in the outer ring all have a negative charge. So since they're all negative, they repel each other, and they want to be as far apart as possible. So that's why we have this theory, and there's the blanks for that. If you look at your table, you have 5 different types of molecules. These are not the only shapes. These are just the simplest ones that we're going to talk about. This is kind of the exception to the rule because we're not bonding to a central atom. This is linear. It has a 180-degree angle. And this is when we have two atoms bonded to a central atom. Or we could just have two atoms bonded, period. And then the number of unshared pairs of electrons, if we're talking about something that has 3 atoms in it, that would be 0. So if we look at this, we would have the carbon is sharing both of its electrons over here and both of its electrons over here. So it doesn't have any dots up here. So this is going to be a linear model. That would be 180 degrees for the bond angle. If we have something that's a trigonal planar, thinking of 3, trigonal meaning 3 things bonded to a central atom with no unshared pairs of electrons, then we end up with a 120-degree angle. And these all would have to need to have equal angles for it. That would be 120. And then we have something called tetrahedral. Tetra is the prefix for 4. So we have 4 things bonded to a central atom with no pairs of unshared electrons. And that bond angle is a little odd. It's 109.5. And I do want to show you an example that's a little easier to see than this one. That one is drawn so that you can see how we actually draw them. But this is kind of what it would look like right here. You would have the 3 kind of at an angle this way and then 1 up. So you would have 109.5 degrees for each one of your angles. Then we have the bent molecule. And for bent, I want you to put right here water. This is the best example, and this is the one that we see most often. We have 2 things bonded to a central atom, but we have 2 pairs of unshared electrons. And so what happens are these 2 pairs of electrons push those down because they are trying to get away from each other. So when we have a bent angle, it's not going to be linear like this. It's going to be kind of bent down, and that's how I've been drawing water for you. And then we have something called trigonal pyramidal. So trigonal meaning 3, pyramid meaning it's going to have a pyramid type shape. And this is when we have 3 things bonded to an atom with 1 pair of unshared electrons. And if you have 1 pair of unshared electrons, it's going to push these elements down just a little bit. So they're not going to be a nice flat trigonal planar, planar meaning flat. It's going to be a pyramid instead. And I'll have models of all of these so that you can look at them in class. Then we're going to talk about, just very quickly, we've already talked about polar and nonpolar covalent bonds, but let's talk about what polar and nonpolar molecules do. First of all, a polar molecule has to have at least 1 polar bond. And when it does, you're going to have a shape so that there is a positive and a negative end. So here's water. And the way we draw this is we take the positive, this is slightly positive down here. This is slightly negative up here. So we would draw it with a plus sign and then an arrow toward the negative. And then a plus sign and an arrow toward the negative. So that's how you draw on the actual molecule so that you can see that it's polar. You can also just do this. Here's the negative end. Here's the positive end. So the negative end is going to be attracted to the positive end of 1. The positive end of this one's going to be attracted to the negative end, and so on and so forth for polar. And then for nonpolar, we're looking at things. Now, nonpolar molecules can have polar bonds, but they have to either have only nonpolar, or they can have polar bonds right here. They can have polar bonds, but they can't have a charged end. So the polar parts have to pretty much cancel each other out. So if I look at this one, this is polar because I've got a positive end and a negative end. This is polar because I've got 3 positives down here, and then this would be my negative end, but my positives are not being canceled out by that. Now if I look at nonpolar, this is the positive part. These are the negative parts. But if you look at it, they're all going in the same direction away, so they're canceling each other out. Okay, so this would be nonpolar because there's not a polar end. They are all the same at the end. This is nonpolar because you have all 4 directions. You have the same charge. You have the negative charge here, 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 and here with the positive in the middle. So these are canceling each other out. And then this one would be polar because we've got the positive ends down here, and we have a negative end here. So we definitely have a polar molecule. All right, so that's just the difference between polar versus nonpolar. And then the last thing is to talk about, other than polar versus nonpolar, to talk about some other forces that are within a molecule or in between molecules. And intermolecular, it's kind of like interstate traffic. Intermolecular means forces of attraction between molecules. So these are not the ones in the molecule. In the molecule would be this. This is within the molecule. That's intramolecular. This is intermolecular because it's between our forces. So what we're going to do is we're going to talk about, these are different than covalent and ionic bonds. And we have 3 types. We have something called a dipole-dipole force. And this is the force of attraction between the positive end of one molecule and the negative end of another. So when we're talking about a dipole force, we're talking about the water molecule like this, and not the actual molecule itself, but the fact that this end is going to be attracted to the negative end of the oxygen. This is what we're talking about right here, that force between them. Okay, and this is the strongest of the intermolecular forces. So this is why water is polar. This is why water makes beads, pulls in beads together. Hydrogen bonding occurs when you have any molecules that have an HF, an HO, or an HN bond. So anytime we have these bonds with hydrogen, fluorine, hydrogen, oxygen, kind of looks like a D, or hydrogen, nitrogen bonds. And this is because we have a large positive charge on the hydrogen, and it's attracted to an unshared pair of electrons on a neighboring molecule. And once again, this is hydrogen bonding. It's the same type of, it acts the same way, and I'll show you an example of that in class. And then we have London dispersion forces, which these are the weakest. These are really very, very weak. And these are the ones that just result from the constant motion of the electrons, because the electrons are constantly moving around. It's causing a little bit of a negative charge. And it's the only type of intermolecular forces when we have a non-polar molecule. Those are called London dispersion forces. And you don't hear about these a lot, but when you do hear about them, you need to know that they're very weak. And they are the only ones for non-polar molecules. Now, we're going to go over these quite a bit more in class because we're going to do a lab on VSEPR theory. But I want you to answer these questions so you can pause it for each question, and then we'll go over these questions in class.